This is problem question number 11, section 1.7. The question is asking you to describe the bifurcations in a one-parameter family. So some function on the right-hand side, we have an expression that includes just one parameter. And the role of this parameter, as it's added on to this function f of y, will simply be to do a vertical translation. As alpha is positive, it'll move this whole graph upward, and if alpha is negative, it'll push this graph downward. So I've drawn some pictures, and just to get us situated, this very first one is the one that is given in the book, and this would of course correspond to when alpha equals 0. And when alpha equals 0, we see that we have 1, 2, 3, let me mark them, 1, 2, 3 equilibrium points. The first one is a sink, the second one is a source, the third one is a sink. Judging by the slopes, the slope here is negative, it's going to be a sink. The slope of f of y is positive, it's going to be a source, sink. And so at A we have a sink, so arrows point towards A. B we have a source, arrows point away from B, and C again is a sink, arrows point towards it. Well, that behavior is not unlike, if we come down here to this graph, not unlike at all. We still have 1, 2, 3 equilibrium values. I should have also mentioned that in the picture it appears that the height of this local maximum is at 2 and the height of this local minimum is at -2. And so alpha being between plus or minus 2 are going to be the critical values where things will change. In a picture like this one, I've only lowered this graph by letting alpha be a number. In this case, alpha is some number that is smaller than 0. It's a negative number, but it's bigger than -2. We haven't brought this maximum point all the way down. We've just brought it down partially, so alpha has to be bigger than -2 in this case. And again, we see 1, 2, 3 equilibrium points, sink, source, sink. And so we draw the phase lines as sink, source, sink. Well, we let alpha get smaller, and until eventually alpha equals -2. And then we realize we're in this situation where we have 1, 2 equilibrium points. A is still a sink. At A we still have a sink. But B is now a node. It has negative values when you're less than B and negative values after B. So our phase line looks like this. And then finally, when alpha is a number strictly less than -2, this local maximum here is now and will remain below the y-axis, will remain below this axis. And so in this case, we only have one equilibrium point, which again, we'll call that A, and it is a sink. And that means it looks like this. Okay? So in terms of where's our bifurcation, well, the behavior here and here both have 3 equilibrium points, but at -2, when I hit the value -2, I no longer have 3 equilibrium points, I just have 2 equilibrium points. And then finally, once I get below -2 and stay below -2, forevermore I'll only have 1 equilibrium point. So on the next slide, I've already drawn it. Here's a summary of what we've said. When I'm smaller than -2, when alpha is smaller than -2, one equilibrium point that's a sink. At minus 2, alpha equal to minus 2, two equilibrium points. The lower one is still a sink. Everything flows towards it. The upper one is now a node with negative values above it and negative values below it. When I'm in the range, as we looked at when alpha was 0, for example, here alpha 0 is between negative 2 and positive 2, we always have 3 equilibrium points. That was the graph we were given originally. And in the lowest one, of course, is a sink. The next one is a source. Everything flows away from it. And the rightmost one is a sink, which is the rightmost one. The pictures down here correspond to these two phase lines, these two pictures. This is the case where I let alpha equal 2. So I've done a vertical translation. I've pushed the whole graph up 2 units until this local minimum is just tangent with the y-axis. And that is a node. But to the right, there is a sink, which will remain a sink, no matter how much we translate this graph vertically. And so I've drawn it here. Here is A. A is a node now. It's positive before you get to A, positive after A. But C is a sink. The solution is moving towards C and towards C on both sides of it. In this final picture where alpha is bigger than 2, I've now lifted this local minimum above the y-axis. So my values all through here are positive, 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 all the way until I get to C, which means I would draw positive values here. And this node corresponds to C. And on the other side of C, the slopes are, the values are negative, and so I draw a negative arrow. And so I would conclude that the bifurcations occur when alpha is equal to minus 2 and when alpha is equal to 2, because to the left and right of those values, so for values of alpha smaller than minus 2, I only have one equilibrium point. At alpha equals 2, I have exactly 2 equilibrium points, and for any value, well, bigger than minus 2 but less than 2, I'll have 3. At 2, if I keep increasing up to 2, I go back to just 2 again. And as soon as I'm bigger than 2, and forevermore for alpha values always bigger than 2, I have just one equilibrium point. So these are my bifurcation values, and that's the end of the problem. Thank you. Bye-bye.